Heidi-ho. Heidi-ho. It's like, Heidi-ho, little campers. Yeah, so I'm back. Put on a sweater. I walked actually about 2 miles because I had to burn off some energy and I'm still all kinds of twitchy. No, it's not coffee. I kind of want coffee. Anyway, time to do this chapter 2 video so that I can do your scientific method lab video and the lab safety video. And then I think mostly that will be everything for your class, I hope. Anyway, bear with me on this one. I have used the same PowerPoint that I made for chemistry. I've used the same PowerPoint since, I think, 2012. I've done like little updates here and there, and I had all my own little commentary, my own little style, but since, again, brand new textbook, I'm trying really hard to be a little more grown up, less cartoony, a little more serious. So I'm really trying to make it match your textbook. So I'm using the textbook PowerPoint, slightly adjusted. I deleted some stuff. I added a couple of things. So if I'm a little like, it's because imagine teaching or talking about something exactly the same way for 8 years and then suddenly changing it. So yeah, bear with me, and that's going to happen a lot this quarter. Sorry. Okay, chemistry. So will rising atmospheric carbon dioxide harm coral reefs? That's the question. We answer it at the end. I will go ahead and tell you right now, spoiler alert, yes. Just so you know. And anyone who had me for environmental science should hopefully already know this. So, intro. How might a chemical compound in the air harm coral reefs? Well, has to do with chemistry. What happens is carbon dioxide in the air, it dissolves in the water, it reacts with the water, form an acid, and then that makes the water more acidic. When the water is acidic, it breaks things down. So again, chemistry. We're going to talk about acids and bases in a little bit in this PowerPoint. So life's chemistry is tied to water. Water is bizarre. It's phenomenal. It's very unique in what it does. Life first evolved in water, and all living organisms require water. It doesn't matter what you are or where you live, you need water to survive. And our cells consist of about 70% water. When we get farther in and you see the cells, you'll see what we're talking about there. So this PowerPoint, the book, likes to do big ideas, and it shows you some of what we're going to cover, and then it goes through. Sometimes where you see it says figure 2.0_1, it's like huge. Other times I take it and I make it smaller at the bottom. I try to still leave it in there so you always know where to find it in case you want to find it in your textbook. But having it huge up in the corner like that, I find very distracting. So as I do more of these PowerPoints, I will probably be making it small and at the bottom. Anyway, here we're going to talk about elements, atoms, and compounds. We're going to talk about chemical bonds and about how cool water is with the life-supporting properties and stuff. So starting with elements, atoms, and compounds. I'm like seriously going to miss some of my pictures here because it used to be when I talked about the atoms, I talked about them being the building blocks of life and likened them to Legos. And I had a picture of my youngest at a birthday, or on a birthday. I took both my kids to what is now called Disney Springs. At the time, I think it was called Disney Village. I don't know, but now it's called Disney Springs. They have a big Lego store there, and I miss seeing the picture of them standing there with all the Legos behind them. But anyway, so organisms are composed of elements usually combined into compounds. So for this, you need to understand what compound means. Compound is the substance containing of 2 or more different elements in a fixed ratio. That's the big part, fixed ratio. So when you learn about water, you probably already know H2O. It means 2 hydrogens, 1 oxygen. Water will always be H2O. Always, always, always. So that would be a compound. Salt water would be a mixture because you can vary how much salt is added into the water. So, yeah, that's a good example. Living organisms composed of matter. Everything alive is built up of a whole lot of things, pretty much. So that's what the matter is. It matters. Anyway, matter is composed of chemical elements. About 25 elements are essential for human life. What it means by essential, it means that the human life cannot continue without. And essential, like when we cover vitamins, minerals, stuff like that, I actually think we cover that in Bio 124. Like essential fatty acids means it's fatty acids your body needs, but your body does not create, so you have to get it from outside. So that's what that is. Now, 4 elements make up about 96% of the weight of most living organisms. Here, we're doing a checkpoint question. It says, explain how table salt illustrates the theme of emergent properties. Basically, it's just saying, hey, look, these suckers come together. You have sodium, which is explosive. Actually, if you take straight up sodium and drop it in water, it's really cool. Wish we had it, wish we could play with it. That would be a whole different lab safety video, probably. Chlorine. Chlorine, yeah, it's like what they put in the pool to break things down, something you are not supposed to drink, you're not supposed to consume. It can make it harder to breathe, can make your eyes red, that kind of thing. Which, by the way, if you go to a pool or an area that has chlorine in order to keep it clean and you smell a very strong chlorine, you're like, yes, you can tell it's really clean. Did you know that it's actually the smell of somebody's pee that's making the chlorine smell stronger? Just so you know. So next time you go somewhere and the chlorine is so strong that making your eyes burn and you see all those little kids, that's why. Anyway, you take sodium, you take chlorine, they bond together and it makes sodium chloride, which is table salt. So the two individuals, very toxic, not good for you. The way they bind chemically, something most of us use. So, this one, it's not bad. It's showing how, what breaks us down, all the elements that we make. The one I used to use was how much are you worth? And it put a dollar sign. It said how much each element was worth at the current market value, but the current market value was a few years ago. And I don't know, it amused me. But anyway, this is just showing what you break down as. So we are mostly, and by mostly it just means more than half, 65% oxygen, 18.5% carbon, and then you just kind of break on down from there. So these are all things that do exist in our body. We need it. Trace elements are common additives to food and water. They do this in order to make sure we can actually get it. If you have ever noticed, if you buy the salt with the little girl with the umbrella, what is that, Morton's, I think? A lot of salts say iodized salt. This is an example of the trace elements. There are a lot of disorders from people not getting enough iodine in their diet, but most people don't add iodine to their diet, and so they iodized salt in order to help fill that need. If you purchase sea salt, like actual sea salt, that has a little bit of iodine in it because that's naturally occurring in the ocean. Yeah, there you go. So, fluoride. Fluoride's usually added to water in cities and stuff like that in the dental products to help reduce tooth decay because fluoride has been proven to help keep your teeth from rotting as quickly. This does not mean that an overabundance is a good thing. So it's supposed to be very carefully monitored. You will see some people will pitch a fit saying there should never be fluoride added to water, but it's one of those things where a little bit is extremely helpful, and a lot of times people just don't understand the benefits of the trace element issue. So this is one of those science things. Several chemicals are added to food to help preserve it, make it more nutritious, and or make it look better. I have an issue with that last one, but we are in America and a lot of people do really shop with their eyes. I talk about this more later. I talked about it a lot in environmental science, so anyone who had me for environmental science already knows this. Anyone who hasn't, You should totally take me for environmental science. It's my favorite topic. Help preserve it. That's what a lot of our additives are for, is so you can buy stuff, keep it shelf stable, make it last a little bit longer, that kind of thing. Here is a checkpoint question. So if you get cereal and it says fortified, first one I think of honestly is Total. My mom likes Total, and it tells you that it's fortified for, I don't remember how many vitamins and minerals. And then if you look at the nutrition label, it says 100% down like 8 of them or something. So if you had this and it says it gives you 100% of the recommended daily intake, and that is 18 milligrams of iron, and your body can only properly handle up to 45 milligrams of iron before it causes your gut to be like, that's what, by the way, gastrointestinal upset just means. It's messing up your stomach. Stomach ache, diarrhea, constipation, anything having to do with this area. How many bowls of this cereal would you be able to eat? And I shouldn't say bowls. How many servings of this cereal could you eat before you exceed the proper amount for your body? Well, all you have to really do is 45 divided by 18. So this would be about 2.5 servings. So if you are not measuring your servings and keeping track of it, you need to be careful if you buy the ones that say that it's got all that in there. I don't see the point in buying any cereal that says 100% of anything in one serving, because I don't know about you, the cereal I like, I want a bowl. I don't want like 3/4 of a cup. So I'm probably going to eat more than one serving. And I obviously eat more than one serving on stuff all the time. Okay, I spoke a moment ago about iodine deficiencies. This is an image of somebody who has one. That is a goiter, that giant lump right there. That's because of a lack of iodine. So if this person had lived, like say in the United States, and was using the iodized salt, presumably wouldn't have had this issue, because the body would have been getting the iodine required in order to keep this from happening. Now these foods are all very rich in iron. So say that you had the Total cereal and you maxed out in iron with the one serving, and then you wanted to eat steak or liver, and I really hate looking at it. It kind of actually makes my stomach turn. It looks gross. You would have to be very careful, because you might tip the scales. It might be too much. So understanding how much your body needs is extremely helpful. This also, again, covered in Bio 124. For this purpose, what we're talking about is the way it breaks down chemically, the whole chemical reaction in your body. And then, of course, we have mouthwash and toothpaste that has added fluoride. And I just think it's funny that this image it looks like it's Aquafresh, and I have not seen that in ages. All right, now, if you remember, like we're paying attention and can remember with all my rattling, about me talking about atoms being the building block of life, here you go. Atom is the smallest unit of matter that still retains the properties of an element. So you have the elements, and then you have your atoms. Atom, teeny tiny little thing. This is what's starting everything up. 3 subatomic particles are relevant in our discussion of elements. We have neutrons and protons and electrons. Neutrons and protons are in the nucleus. That means the middle. And the neutrons are neutral. So if you can just remember neutron, neutral, neutron, neutral. Say that a couple of times, neutron, neutral. That'll help you. Protons are positive. So P for positive, proton, positive. This means you will see it. It will be identified as a little P and a plus sign. So that will be proton. These are right there in the center. And then we have the electrons. Electrons are negative, and they're orbiting. They're going round and round. They're just kind of spinning all around. These suckers like to move. The unique number of protons is an element's atomic number. So each element has an atomic number to help identify it. Atom's mass number is the sum of the number of protons and neutrons in the nucleus. So you add these. That's all you do. Atomic mass is approximately equal to its mass number. Isotopes of an element have the same number of protons but different number of neutrons. We will talk more about isotopes in a moment. I think there are some pictures. Now, if we were to look at this and we said a nitrogen atom has 7 protons and its most common isotope has 7 neutrons, a radioactive isotope of nitrogen has 9 neutrons. What is the atomic number and mass number of this radioactive nitrogen? Well, if it actually has 9 neutrons, then this is going to make it slightly negative, right? No. I don't know why I said slightly negative. Neutron is neutral. You would look at this and say, I got lost in the question. Radioactive isotope of nitrogen has 9 neutrons. Atomic number and mass number, sum of protons and neutrons. So the regular one, 7 plus 7 would be 14. If you say it's radioactive and it now has 9 neutrons and we are adding the protons and neutrons, that would be 7 plus 9, so that would be 16. Mass number, approximately equal to its mass number, is the atomic mass. Should be the same. I wish I could remember if this has a periodic table. We'll get to a periodic table, I think parts of them in just a moment. Again, getting used to this PowerPoint instead of the one I normally have. So here they're trying to show you it. The pink are the protons. That's where there's a plus sign. Remember, protons positive, and yes, I will ask you that. We have 2 protons, we have 2 neutrons, and then you see 2 electrons. You have the protons and the neutrons in the middle. That's your nucleus. And then you have the electrons going all around. The reason this shows an image, says the electron cloud, that's just where the electrons are spinning all around. These suckers are moving. They do not just sit there and hang in place. They're all over the place. Okay, now, carbon 12. Protons 6, neutrons 6, mass number 12. Carbon 13, protons 6, neutrons 7, mass number 13. Carbon 14, protons 6, neutrons 8. So the mass number is 14. So again, you just add the protons and the neutrons together to get your mass number. Then electrons, they all have 6 electrons. They all still have 6 electrons. That does not change. So radioactive isotopes, these can either help us or harm us. Radioactive isotopes are useful as tracers for monitoring the fate of atoms and living organisms. We're about to have 2 examples of this in just a moment. One that's in your book and one that I kept from my previous stuff. We have very sophisticated instruments to take pictures to see it, which again, you'll see in the pictures in just a second. There's also dangers associated with using radioactive substances. Mainly, radioactive can kind of knock things out of whack. This is why when you get an X-ray, they try to cover you with the lead apron to try to protect your body from the radioactive. So here's yet another checkpoint question. Why are radioactive isotopes useful as tracers in research on the chemistry of life? Here we have some images. This one is showing the, I never know whether to say it's a PET scan or a CAT scan. But anyway, you go in, or maybe it's an MRI. Listen to me. You can tell I am not a medical person. So here, the person goes in there and they hear, thunk, 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 thunk. If anyone's ever had one of these, you totally know what I'm talking about. It's taking all these images and it's lighting up the sections of the brain. It's looking for something in very, very particular. So here's an example of the brain. This person you have over on one side, I guess I should say this one right here is a healthy person. Notice you've got the blue, you've got the purple. So this one, the chemical that they had them consume in order to light up the brain when they took these images showed this is the healthy brain. The other one is the Alzheimer's patient. Notice not as much blue. It's not nearly as calmed down. It's like stuff everywhere. This is how, just by doing a certain brain scan, they can say whether or not somebody is like early stages of Alzheimer's or this part's showing up, that part's showing up. It's because it's causing certain things to light up. This is the one that I use from my other PowerPoint because I find this one fascinating. They use 2 PET scans to show the activity of this one particular molecule. MAOB. We have a non-smoker and we have a smoker. I labeled them underneath so you know which one's which. Activity is color-coded from red being the highest activity to purple, which is the lowest activity. Low MAOB activity is associated with violence, impulsiveness, and other behavioral problems. I mention this because first look at the brain. If you look at the brain, you will see that purple is the lowest, and you will notice that the smoker has nothing but purple. I think you know that if you're smoking, you do tend to, your body's making adjustments, for lack of a better phrase. You have these receptors that are like wanting that nicotine, something fierce, and that's pretty much what's going on. So it's literally altering your brain chemistry. Now, if you look at the lungs, they're harder to spot, but you can actually make out some lungs for the non-smoker. For the smoker, it's just gone. But I think you also probably know if you're smoking, you're kind of killing sections in your lungs. We talk about this more also in Bio 124 when I talk about the cilia inside your lungs, and when you're smoking, how you're literally burning them and stuff. Okay, look at the heart. There's actually some activity in the heart for the non-smoker. The one for the smoker, it's a lot lower. So that means this molecule is not nearly as active in the heart. And more people who are smokers tend to have heart issues versus non-smokers. But the real one I want you to look at is the liver and the kidneys. They're the fascinating ones. The liver, much more lit up, but the kidneys, holy crap, look at the kidneys. You have bright red active in the kidneys for the non-smoker. For the smoker, you've got some green, blue, and purple. So it's not working as well for the smoker. And the reason is, and why I point to these, is your liver and your kidneys are there to clean your blood. They're cleaning the toxins out. That's what's helping keep you healthy. And by smoking, you're basically killing off a lot of the stuff that's helping protect your body. So it's not just a cancer issue, it's an entire circulation and healthful issue. So there you go. Chemical bonds. Distribution of electrons determines an atom's chemical properties. So for these, the electrons, they're going to be in different electron shells. You saw the electron cloud a moment ago, and I keep saying that they just spin like this. Well, they have these literal shells. Well, not literal shells. They call them shells because it's a certain amount in each spot. These electron shells are how they decide if they're going to connect to another electron and form chemical bonds. Well, it's not that they connect to another electron, they connect to another atom. Anyway, it's how they join because they do not like to be alone. They like to be in pairs. So we have a hydrogen, and we'll see pictures in a minute, but the hydrogen has one electron. That's why if you look at the periodic table of the elements, and when we're in class, it's right on the wall, hydrogen is 1, H1. It has one electron just spinning all over the place. And that hydrogen will hook up with everything it possibly can. I tend to refer to it as the promiscuous atom because he's the player. Hydrogen just wants to be connected to every possible single he can find. And easily broken, bounces right on over to another one. Hydrogen bonds are very important. We'll get more into that. But if you can just remember, for the electron shells, they like to be paired. So if there's an odd number of electrons here, it's always looking for another odd over here, so then they can join together and be paired up. Checkpoint question again. Looking at the electron distribution diagrams for hydrogen, oxygen, nitrogen, and carbon, how many covalent bonds can each form? Well, I don't have the pictures right here, but if you're in your textbook, you would have it, and then you could answer your questions. So here we go. Notice we have the nucleus is in the middle. That's where we would have our protons and neutrons. Then the inner shell, we have exactly 2 electrons. You can never have more than 2 electrons in that inner shell. Once you have 2, you go to the next shell. And here it has 4, but you can get up to 8. So you can have 2, 2, 2, 2. Once you have 8 electrons on that shell, you go to the third shell. And then that you can have 8. And this is actually how you can predict how many you have, what it's going to connect to. So here is the first part of the periodic table. Notice again, hydrogen, you have 1 electron in the first shell. Helium, you have 2 electrons in the first shell. So on the periodic table, it's hydrogen 1, helium 2. Second shell, you have, notice all the way across for the second and the third shell, you have 2 electrons in the middle. You always have 2 in the middle. Then the next one, and I say middle meaning the one closest to the nucleus. That would actually technically be inner. Look at your second shell, and then notice lithium has 1, and so that would be 3 because that's 3 electrons. We are now looking at carbon, nitrogen, and oxygen. Carbon, you have 2, 3, 4, 5, 6. Nitrogen, you have 4, 5, 6, 7, and oxygen, you have 8. Literally how you count these. When you look at neon, you will see that there are 2 in the first shell. You will see there are 8 in the second shell, and shoop, they come over here to the third shell, and now sodium has an extra. We talked before about sodium and chlorine, so I am going to use this little laser pointer to point something out. Sodium, notice we have that one lonely little electron here just floating around going, I am so alone. And then over here, look, there's another one. This one also has one lonely little electron. That is part of what makes it where they can bond as well as they do. So, we already looked at this. Now, covalent bonds, co, as in both. So you will hear me say this a lot, like especially when we get to genetics, I'll say co, as in co-captain, or as in co-ed. Co means 2 at the same time. So covalent, valent is where the electrons are, that's the valence. So covalent bonds joins atoms into molecules through electron sharing, so they're sharing. Non-polar covalent bonds, they are shared equally. Polar means they are not equal. This means there will be a small charge. So non-polar, perfectly even. Polar, there's going to be a charge. So, checkpoint question. Polarity refers to a separation of charges. Explain why the bonds in a water molecule are polar covalent bonds. Well, it's because we have 2 hydrogen, we have 1 oxygen. That's pretty much it. We'll have pictures of that in a minute too. So, I don't know. This is my first time seeing a book where they do the little electron cloud. I think it's kind of cute, but doesn't really do much for me other than I think it's kind of cute. So, here we go. Yeah, I had a whole section talking about these in my other one, but this puts it all together. So we have our 4 common molecules. We've got the name across the top: hydrogen, oxygen, methane, and water. Now, molecular formula: H2O2, because these are binding to each other. I'll explain that in a minute. CH4 and H2O. I guess I should use my little laser pointer again. I like this. Okay, so notice these 2 individual bonds, electrons, they bind together because remember the hydrogen. It's a lonely little sucker, wants to be hooked up. Couldn't find anybody else, but there's this other hydrogen, so they go, so they connect. So we've got the 2 electrons. Oxygen. Oxygen is always going to bind twice. There's always going to be 2 attached to an oxygen. So if you have 2 oxygens together, it will be a double bond. So for the structural formula for hydrogen, notice it's just a dash because it's only one bond. Oxygen is a double bond. So again, 2 electrons, 4 electrons. That's the big thing to notice. Now, carbon always wants 4. Always wants 4. Carbon is greedy, wants 4 bonds. So you can have 1 carbon and 1 carbon, and you're going to have 4 bonds attached to each other. But here's the more common one right here. Because each hydrogen only binds once, you can attach 4 hydrogens to 1 carbon. Make sense? I hope so. And then here is our water molecule. Again, hydrogen can only bind once, but oxygen wants 2. So you can have 1 oxygen attached to 2 different hydrogens. And that is pretty much how that works. I guess I could have covered all this as I went through these PowerPoints. So sorry. The space filling model is supposed to show you how they share the electrons. They just look like stress balls to me. I don't know. So now here is the water thing where it says slightly polar. Both of your hydrogens are positive. Your oxygen is negative, and so it's slightly polar. Slightly. This is showing us about, again, covalent bonds and about how they attach. This is a video. I could play it, not going to. I'm trying to shorten this, even though I have like rattled on and on and on, and I still have a bit to go. However, feel free to watch these videos. They are in the book PowerPoints, and they're still obviously in this PowerPoint. If you watch this in slideshow mode, you can click. So when you see a bar like this, just go there and click the button and it will play the video for you. Now, an ion is an atom or molecule with an electrical charge resulting from the gain or loss of 1 or more electrons. So it means it's a plus or minus. There you go. If you have ever played with magnets, that's kind of what this is like. So imagine you have 2 magnets, this one and this one. This is positive, this is positive, this is negative, this is negative. If you take these 2 magnets and you try to push the 2 positives together, it does this thing. It's like there's a force field. It's trying to push them apart. I used to play with magnets all the time. I love them. But if you take these 2 magnets and you're trying your hardest to push them together, and it's like, you can't quite make them touch unless you force it, and then as soon as you let go, they bounce. But if you just turn it like this, so it's positive, negative, it goes and it attaches. That's pretty much how these work. So positive and negative. So when you have 2 ions with opposite charges, boom, they attach to each other. So this is how we do our salt. So the sodium chloride, that is how we get our table salt. So checkpoint question, explain what holds together the ions in a crystal of table salt. Well, again, sodium ion, positive, chloride ion, negative, ionic bond. They attach to each other. And here it's trying to show you. So again, these hydrogens, they do not like to be by themselves. I mean, these little electrons, didn't mean hydrogen, electrons do not like to be by themselves. So this electron goes, oh, look, there's a friend, and it goes shoo and goes running over there, which causes a sodium ion. And then we have our chloride ion. Why is the chlorine atom called chloride? Don't ask me. That would be for a much more in-depth chemistry class. We only do 1 chapter of chemistry, so we keep it as simple as possible. So your sodium ion is positive, positive. Chloride ion, negative, connects. We now have sodium chloride, table salt. And then they're just trying to show you the picture. Video again if you want to learn more. Okay, one of the most important types of weak bonds is the hydrogen bond. I talked about this already. I said this is the promiscuous atom. This is the one that hooks up absolutely everywhere. Hydrogen atoms of a water molecule are attached to oxygen by polar covalent bonds. Again, talked about that just a little while ago. Because these polar bonds and the wide V shape of the molecule, the water is a polar molecule. I'm having a hard time with words. So remember, we had the oxygen here, and then it branched off, and here were the hydrogens. It doesn't go straight across. It actually is slightly angled, and so it gives us a slight polar. So what enables neighboring water molecules to hydrogen bond to one another? Well, it is that promiscuous hydrogen. It's because the hydrogen bond is a very weak bond, and that hydrogen is always looking for the next conquest, the next buddy, the next anything. Again, it's a player. So this hydrogen's with this water, but he's looking over here. That one's like, hoo, 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 and then jumps over to that one, and then this one jumps over to that one, and ding, 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 ding. That's also actually part of what gives water that nice liquidy everything. So the hydrogen bonds constantly being broken and reattached. Animation of water structure. The ones I used to show you for the water structure is I showed the difference between the steam, the liquid water, and the frozen, the ice. Because the main difference is how fast or how slow the hydrogens are bouncing or jumping ship, how fast they're switching. Regular liquid water is like ding, 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 and that's why it's liquidy. If you've ever noticed when your water is very, very cold, it's like getting towards slush, it doesn't go as fast as a hot water. It's because it's taking the bonds a little bit longer to break. Ice, they're kind of frozen in place. That's why once it's completely frozen, it's all just kind of like this. It's also why ice is less dense. This is why ice cubes float, because it kind of froze like this, like a lattice work. Basically, imagine this hydrogen's like, I'm going over here, and then froze in place. He's on his way changing to another partner, but doesn't quite reach there, and everything just kind of stops. So it's a little stretched out, for lack of a better phrase. Meanwhile, if you boil the water, the steam rising off of it, if you put your hand over it, it will get wet because you're feeling it's actually water that's rising from the steam. And this is because when it gets really, really hot, those bonds are forming like this. And that's part of what makes water so freakishly interesting when you talk chemistry-wise. So formation of water from hydrogen and oxygen is an example of a chemical reaction. Chemical reaction means you're taking stuff, putting it together, and making other stuff. So what happens here is you have your reactants. That's what you're starting with. Then you have the arrow that tells you where you're going. And then that ends up in a product. Product, kind of like if you remember any of your math terms, when you multiplied this times this equals that, that was your product. So like 2 times 2 equals 4. You would say the product of this is 4. Same kind of thing for your chemical reactions. Now, chemical reactions do not create or destroy matter. They only rearrange it. The important thing here is to know all of it has to be accounted for. So, example here. We have carbon 6. This number here means there are 6 carbons. So now you look over here and see this C. Ooh, can I write on this? Let's find out. I think I can. I've never done this, so bear with me if it's horrible. Okay, so if we have 6 carbon and we have a 6 here, then we would need, there we go, woo, 6. 6 carbon on this side, 6 carbon here. Now, 12 hydrogens. So let's look over here. We have 2 here, so that's 2 hydrogens. So if we have 12, what is 12 divided by 2? Well, that would be 6. Right? Yes. Okay, now we have 6 and we have O, and we have 6 and we have 2O. That means this times that, so that would be 12 plus 6, so that is 18 oxygen on this side of the arrow. So we need to have 18 oxygen on this side. Is that right? I think that's right. 12, 13, 14, 15, 16, 17, 18. Yeah, it should be 18. So this should be, I think my notes are wrong. Wouldn't that be 12? Oh, no. See, I'm totally messing myself up. This would be a 6 because I was forgetting that part. So we have, we have here 6 oxygen, and this is 12 oxygen, so that's 18 oxygen. This is 12 oxygen, that is 6 oxygen, so that is 18 oxygen. Here we have 12 hydrogen, here we have 12 hydrogen. Here we have 6 carbon, here we have 6 carbon. So everything that is in the reactant side is accounted for in the product side. You just have to be really careful because like you just saw, I was totally messing it up going, what? Because I forgot about the 2. I actually kind of have fun with the chemical reactions like this. I like balancing them, and I don't know why, but I also do math things just for fun. So there you go. Here we go. This is showing you a picture of our 2 reactants, the reaction, which is the arrow, and then the products. Now we are to water. Woo! So, tendency of water molecules of the same kind to stick together is called cohesion. It means it's sticking together. Remember, co-captain, together. So cohesion means water molecules together. A tendency of 2 kinds of molecules to stick together is adhesion. So like adding something to it. A good example of this would be back in the day when we went to restaurants, if they come up and they put your drink down there and it's very, very cold and you notice there's water on the outside of the glass. The water on the outside of the glass, that would be cohesion. If you took a straw that was still wrapped in paper and you attach it to the side, you just kind of like balance it, and then the water connects to the paper of the straw, that's adhesion. I used to do this when my kids were little all the time, and I said it was magic. I'm like, look, I can make it stand next to the glass. They thought it was really cool until they got old enough to know it wasn't really anything special. And then I had to admit I'm not a magician, but whatever. It was fun. So cohesion, together. So cohesion is the water molecules together. Adhesion is adding something else to that. So cohesion related to surface tension. This is how, a measure of how, this is why it's hard sometimes to break the surface of a liquid. I'm going to talk more about that in a second. First, we're going to do this checkpoint question. After a hard workout, you may notice beads of sweat on your face. Can you explain what holds the sweat in droplet form on your face? Well, we already talked about the cohesion. The cohesion is what's making the sweat beads form, but adhesion is what's holding it to your skin. Now, for the surface tension. I think these are fascinating. The picture I used to have I liked more because it showed a shadow underneath, but this is a really, really good shot because if you look where the legs are, you can see it looks almost like the water is dipping just a tad. That is because of the surface tension. That's cohesion. That is the water trying to hold together. It's the reason why if you smack the water with your hand, it goes tsh, it doesn't just go whoo. If you go like this, it makes a noise. If you go like that, you go straight through, that kind of thing. It's also the difference in doing something else like this. Clearly, I added this one. This is the difference between a belly flop and a dive. If you have ever jumped into a pool, if you did the proper dive, and you notice they always do this with their hands, it's because they are basically doing a gentle thing to help separate the water bonds. If you just go poof, it hurts, and you can get bruised. So a belly flop, wonderful example of surface tension of water. Okay. Animation showing you how it's the cohesion and adhesion properties of how a plant brings nutrition and water up into itself. Now, heat. Heat is absorbed when hydrogen bonds break and released when the hydrogen bonds form. So this is what helps keep temperatures relatively steady. As the most energetic water molecules evaporate, the surface of a substance cools. I think I remember there's a picture coming up that shows this happening. So when it's evaporating, the surface of the liquid that remains behind cools down because the heat is coming off of it. This is the reason why, I guess a good example for this would be a hot pan. If you have just been cooking and you don't realize you are supposed to let your pan or your pot cool down before you put it in water, which by the way, you're supposed to in order to extend the life of your pan. But if you take the pan, you I don't know, say you made eggs, you put the eggs on the plate and then you go over to the sink and you put the pan underneath the water, it goes, you see all that stuff come off. That is the water evaporating off of it, trying to help remove the heat from what was behind. That's why it cools down so fast. So, checkpoint question. Explain the popular adage, it's not the heat, it's the humidity. Oh my gosh, we live in Georgia. You know this is true. It's not just hot, it's humid. The humidity is what kicks your butt. If you have ever been out west, Arizona, Nevada, places like that, it's a very dry heat. And I know before I went, I was like, psh, 100 degrees is 100 degrees. It's still friggin' hot. And yes, it is hot. But 100 degrees in Vegas is different than 100 degrees in Atlanta. And it has to do with the humidity. It's because the humidity makes it so much harder for the water to evaporate and to take some of the heat with it. This is why when it's super humid outside, you're just like, oh, and you are just like coated in sweat. You're just like drenched. But if you are in a more dry area, you might be sweating, you're still losing the moisture, but it's actually coming off of your skin. You're not like soaked. That's pretty much what that is. Oh, here's the image I was talking about. A dude, exhausted, hot beyond belief. And look at that, you see steam coming off his head. It's because it's cold enough out there that you could actually see it. I just think that's pretty cool. Okay, ice floats because it is less dense than liquid water. I already talked about this. I already talked about how water is a gas, a liquid, or a solid. That it's less dense as a solid because of the way the hydrogen bonds. So already covered all this. I talked about it earlier, so we can just jump right past that to the checkpoint question. Explain how freezing water can crack boulders. This is why tiny little cracks are so important to keep track of. Because the water gets down into this tiny little crack. This happens a lot on streets and sidewalks. It rains, the water gets down in there, and then the temperature drops below freezing. Well, those hydrogen bonds, it goes like that. Whatever you freeze is going to freeze a little bit larger than the liquid form. And it has to do with the way the hydrogen bonds are moving around. This is why if you fill something with water and then you put it in the freezer, it's always a little bit bigger. I don't know if you ever noticed that, but test it out. Take an ice cube tray and put different amounts of water in each ice cube tray. Mark exactly where it is and then freeze it. And you will notice it always freezes a little bit above your water mark. It's kind of cool. So this is just showing you the liquid water and the ice, the solid water. So again, the liquid water, hydrogen bonds constantly breaking and reforming. In the ice, they're just stuck in place. Now we are to solutions. Water is the solvent of life. A solution is a liquid consisting of a uniform mixture of two or more substances. So if you remember a moment ago, like at the beginning, I told you the difference between a compound and a mixture. And I said a mixture is like you're mixing the two things together. And I said salt water. Now I'm going to talk about sugar water, because if all goes well, in week 3, we get to do one of my favorite labs, and we will be working with sugar water. So I'm going to use that as an example when I talk here. Solution of that would be a solution of sugar water. So you might have 20% sugar, 80% water. That would be a solution. Water's versatility as a solvent results from the polarity of its molecules. This means it can connect and reform, it can blend in that stuff very well. Polar or charged solutes, which is what gets dissolved in the water, form an aqueous solution. So solvent would be the water. The sugar would be the solutes. I always have the hardest time with that word, gosh. So if I'm talking about a solution of sugar water and I said it's a 20% solution, that means 20% solutes, so 20% sugar, and then 80% is the solvent, which is the water. Now, checkpoint question. Why are blood and most other biological fluids classified as aqueous solutions? Because it's water. That's why the solvent is water. And this is showing you, this is showing you the salt water. See, if I'd stayed with salt water, we would have had the picture right set, and it would have been like, oh, look at me, I did it right. I'm getting distracted because I swear I think I just saw a chipmunk. I hear something, but I don't know if it's a chipmunk or a bird. Waiting to see. And my cat's not doing anything. Okay, so chemistry of life is sensitive to acidic and basic conditions. Yeah. So in liquid water, a small percentage of water molecules breaks apart into ions, and we just talked about ions a moment ago. We use the pH scale to describe how acidic or basic a solution is, and a buffer will minimize the changes in the pH. We're about to look at acidic and basic in just a moment. First, we will do this checkpoint question. So, compared to a basic solution at pH 9, the same volume of an acidic solution at pH 4 has blank times more hydrogen. Hydrogen ions. This, if you're looking in your textbook, hopefully it will have shown you how to calculate this. The answer is actually 100,000. So it's a huge change. Hopefully you'll see it in your book. But here you go. This is what I wanted to get to. So why they do it this order, I don't know, but they do. So pH scale 0, that is the most acidic. That is corrosive acidic. This means it has higher hydrogen ion concentration. Battery acid, you know that's going to be acidic. Most people know lemon juice and your stomach acids are acidic. I mean, hello, it's in the name, acidic. Now, as you get closer to 7 is neutral. Nice and simple, neutral. That's pure water, that's your human blood, that's your tears. Your urine and your saliva is a little more acidic than your blood and pure water, but it's still close in range. But neutral, that's why it's a good buffer, that's why it works great as a solvent, that is our pure water, and again, human blood. Then we start to get basic. Basic has less of the hydrogen ions. And so here, notice it has the OH instead of the H. 10, we have milk of magnesia, 11, ammonia, 12, bleach, 13, oven cleaner, 14 is the most basic. So notice, if you will, we have positive and negatives shown here. So if you look at number 2 on the pH scale, something very acidic, that would be the gastric juices. So imagine you have an upset stomach. And now I have that Pepto-Bismol commercial running through my head, the whole friggin' song. But anyway, imagine you have an upset stomach and you have heartburn. Indigestion. Okay, anyway, imagine you have heartburn. It's like, oh, and it's all kinds of acidic. And then you take, shall we say, Pepto-Bismol. That's a type of milk of magnesia, which is basic. So you are taking a base to bring your acid down. So you're literally just trying to balance it. Yeah, I think that's about all I've got for that. That's just showing you, again, closer up pictures. Now, this has been a long lecture. Scientists study the effects of rising atmospheric carbon dioxide on coral reef ecosystems. Well, carbon dioxide is the main product of fossil fuel combustion. This is what's constantly going out there every time you're running the car. Increasing in the atmosphere, yeah, we have a lot of carbon dioxide in the atmosphere. It's not good. And linked to global climate change, otherwise known as the current climate crisis. These are all facts. About 25% of this human-generated carbon dioxide is absorbed by our oceans because our oceans cover most of the planet. And so as the ocean absorbs this carbon dioxide, it is flipping the switch and it's turning it into being a little more acidic. I don't know why I couldn't remember the word acidic, but it's being a little more acidic, and that is what's known as ocean acidification. And I'm planning on trying to test out a lab in Bio 124 about this, where we are going to put things like shells or something into a type of acid like vinegar and see what happens. So we're going to try to do our own ocean acidification in Bio 124, but this is 123. I just want you to know what it is. Yeah. So seawater acidifies the extra hydrogen ions combined with carbonate ions to form bicarbonate ions. And then this reaction reduces the carbonate ion concentration that's available for the corals and other shell-building animals. And this is what breaks down the shells and the coral. So, in controlled experiments, scientists looked at the effect of decreasing carbonate ion concentration on the rate of calcium deposition by reef organisms, and what they found is it brings it down. It makes it less likely for the coral animals to actually grow. Because yes, coral is an animal, believe it or not. It really is. It's not just a rock. So it's living things, and it needs to process properly. So basically it's destroying it. So we are looking at this. It's a graph trying to show you the calcification rate. So being able to calcify, produce the calcium, make it harder, make the shells. And then the x-axis, so that's the y-axis. The x-axis is showing you the increase. Sorry, I thought the cat was coming. Like, what is that? So here you go. Checkpoint question. Identify the independent and dependent variables. So independent is the x-axis. That is what is in the seawater. The dependent, what is depending on what's being adjusted, will be your y-axis. That is the calcification rate. Way easier to go over this with more individualized lessons, but there you go. So this is just showing you the rising carbon dioxide bubbles lower the pH of the water. This is actually causing the acidification. When it says lower the pH, that means the number itself is going lower. So instead of being fresh water is 7. So, but instead of being in that general area, it's going like 6, 5, 4, 3, that kind of thing. So it's turning into more of an acid. Oh, and let me just go ahead and throw this out there. There are a lot of products, a lot of feminine hygiene products, where they sit there and say it's pH balanced for you. Just so you know, you don't need to ever purchase those unless you just like it. A deodorant or a soap or anything is not actually going to make your balance perfect or anything like that. Your body naturally stays right around the proper neutral zone. That's what your body does. If you are so out of whack that you feel the need to have a pH balanced something, or you think you have to drink alkaline water in order to bring your acidification down, Chances are there's an issue. A doctor would actually prescribe it. So unless a doctor is telling you specifically that your pH is out of whack, just save your money and don't buy into the hype. Just, so you know. Okay. Whew, almost done. Search for extraterrestrial life centers on the search for water. Well, it's looking for water because most of the stuff having to do with water is what supports life here on Earth. And so we kind of think it's probably contributes to potential life to have evolved on other planets. This is why when they talk about, oh my gosh, is there life on Mars? And then if you see any articles, they're like, oh, we found water on Mars, because our assumption is since everything on Earth needs water, that would be the same. That's pretty much it. It's because we know water as being what's important for everything for life. It's our solvent. It's in everything. So without water, we can't survive. So we just kind of assume water is needed anywhere else for life. So that's pretty much it. Now, you should be able to do all of these things. If you can't do this perfectly right now, that's fine, because I can only say so much. You should also be reading the book, looking over it, and making sure you understand these things. I think, yeah, that's where it ends right there. So that's it. We have now done our chemistry video. Next up, I shall be doing the lab videos. Wow, it's already been a long day, and it's Monday, and I have not even had lunch yet. It is 12:16 as I finish this up, and I'm tutoring at 1, so I better get busy on this, huh? So I guess that's it, and see you in the next video.